So excluded minors can give an alternate description of minor closed class. So in an effort to characterize real representability, we'll look at the excluded minors for real representability. Unfortunately, in contrast to over a finite field, we find that there are infinitely many excluded minors for real representability. However, this doesn't say anything about the complexity of the excluded minors. It still might be possible to have a nice characterization. For instance, we can nicely characterize bipartite graphs by excluding odd cycles, even if there are infinitely many odd cycles. However, we have this remarkable result due to Mayhew, Newman, and Whittle, which says that any real representable matroid is a minor of an excluded minor for real representability. So this suggests that the class of excluded minors for real representability is at least as wild as the class of real representable matroids themselves. So this is already vastly different than over finite fields. They prove this by constructing excluded minors that are not representable over any field. So it's still, you might think it would still be possible that the reason for this is because the non-representable matroids are just so wild themselves. Indeed, we have an old result of Knuth that gives us that there are a lot of matroids, and a new result of Nelson says that very few of them are in fact representable. So instead of looking at the general excluded minors for real representability, what if we look at just the representable excluded minors? Specifically, we'll look at the complex representable excluded minors. So we find even in this case, the complex representable excluded minors are at least as wild as the real representable matroids themselves. So I'll quickly go over the construction we used. So starting off with a real representable matroid N, we'll construct a complex representable matroid M that's an excluded minor for real representability and contains N as a minor. And we'll use various operations that preserve representability to construct this from N. We'll also need a property of representability to prove that this matroid will not be real representable. And this is an intersection property. So given two flats in a matroid, if we have that the span of these flats meet at a point in the ambient geometry, then we can add this point to our original matroid to get an extension. And we'll call this extending to the intersection of these two flats. So this is not a matroid operation in general, but you can do this to any representable matroid. So first, start off with a decorating procedure due to Mayhew, Newman, and Whittle, which says that any real representable matroid is a minor of a real representable matroid whose ground set can be partitioned into two bases. So starting off with our matroid N, we freely add two bases. And then for all the original points in the matroid, we'll replace each with a series pair. And this will give us a new matroid N1. N1 contains N as a minor because we can contract one of each of the elements in a series pair and delete all the other points we've added in our two new bases. And this has the obvious partition just into red and green as the two bases of N1. As the other ingredient in the construction, we'll need an excluded minor we already know to be complex representable, and I'm just taking this rank 3 frame matroid. And we also need two distinguished points in this matroid, just P and Q. So with these two ingredients, we have N1, which is our decorated original Matroid, and L, our known complex representable excluded minor. We'll start by taking the direct sum. We will then add a point X freely in the span of N1 and P, and a point Y freely in the span of B1 and Q. We will then lift all the points from one of the bases, A1, towards X to get a new set A. A will also contain X. And similarly, for the other bases, B1, we'll lift all the points freely towards Y to get a new set B, which will also contain Y. And finally, we will delete P and Q to get our final Matroid M. So this Matroid is complex representable because all the operations we used preserve representability. It contains N as a minor because you can just delete all the remaining points in L, contract X and Y, and this will give you back N1, which we already know contains N as a minor. Hence, M will contain N as minor. And to see that it's not view representable, we're going to use the extending to intersection property. So if we extend to the intersection of the flat spanned by A as well as the flat spanned by the remaining points of L, we would be able to retrieve P, and we can do a similar thing to retrieve Q. So if this Matroid was view representable, by extending into these intersections, you could retrieve P and Q to get the original excluded minor L. So that would be a contradiction, as L is not view representable. With a bit more work, you can also show that this is in fact an excluded minor for real representability. As we only used specific properties of representability over an infinite field, this actually holds for any two infinite fields, F1 and F2, where F1 is contained in F2. Specifically, if representability in the larger field does not imply representability in the smaller field, then the excluded minors needed to distinguish between the two, between representability over the two, is at least as wild as the class of Matroids representable over the smaller field. You can also use this construction for other classes. So for example, gamoids. Dylan Mayhew already showed that the excluded minors for gamoids are at least as wild as the class of gamoids themselves. And with this construction, you can also show that even the gamoids that, even the excluded minors that are representable over all infinite fields are still at least as wild as the class of gamoids themselves. And yeah, thank you.
Does anyone have a question?
How big is your Matroid now?
Well, it increases in rank by 3 in this case. The original decorating procedure, you can improve it slightly, but it will essentially double the number of elements, and then it's just a constant number of added, yeah.
Can you give an example of one infinite field that's contained inside another one, properly contained, so that the Matroids are represented by the both of them exactly the same?
Complex and complex with some added thing. I mean, also, yeah, so complex with polynomials over complex. Because the complex numbers are algebraically closed, you should be able to, you can also do other, yeah. Also just, I don't know, if you have polynomials in so many variables, or sorry, the rational functions in so many variables, you could just add an extra one, I suppose, in infinitely many variables. But yes, they're yeah. Sure, yes.